Hello, everyone, and welcome back to another exciting section of functions of two variables. In this section, we're going to study the relationship between the demand of two products using functions of two variables and the sign of their partial derivatives. So the general setup is the following. Suppose we have two products. Let's call them A and B. I know, super exciting. And suppose XA and XB represent the demands of those two products respectively. And suppose that PA and PB represent the prices of those two products respectively. And now what's really exciting here, because we have access to functions of two variables, we can assume that these demands XA and XB are both functions of two variables that depend on PA and PB. So here we're going to start with two functions of two variables, X of A and X of B, and both of them are functions of two variables. So here we go, boom. Okay, so we have these two functions, so X of A, which is going to be the demand of A, and it's going to be a function, or it's going to be modeled with a function where the variables are PA and PB. And same thing for X of B. Is going to be the demand, representing the demand of the product B. And again, this demand will be modeled by a function that depends on the prices PA and PB. And of course, now that we know about partial derivatives, now that we have two functions of two variables, we can study these two functions and study the relationship between those two products using the partial derivatives of those two functions. So here we go. So for both function, 1, 2, 3, boom. Okay, so for X of A, we're going to have the partial derivative del XA over del PA and del XA over del PB. And then for the demand XB, we're going to compute the partial derivatives del XB over del PA and del XB over del PB. And we're going to use actually only the sign of those partial derivatives to see what type of relationship these two products have. And the two type of relationship that we're going to be trying to measure with the models given by those two demands is if these two products are, competitive or complementary. So first, two of those partial derivatives are going to be always strictly negative if the models, of course, are good for those demands. So, for example, suppose that the price of B is fixed and we increase the price of the first product A, then automatically, if the price goes up for the product A, the demand will go down. So this means in terms of partial derivatives, del XA over del PA is always going to be strictly negative. And this is not a surprise. This is just like before, price goes up, demand goes down. It's almost going back to the case of one product with one demand and one price. We're expecting the demand function to be a decreasing function. And then, of course, the same idea for the other product. If the price of the product A is fixed, but we are increasing the price of product B, then of course we're expecting the demand of product B to go down. So here, del XB over del XPB, is going to be also strictly negative. So these two are always going to be strictly negative. Del XA over del PA and del XB over del PB are both going to be strictly negative, because this is almost just simply, as I've mentioned a moment ago, going back to the case of one demand. What happens to one demand of one product when its price is going up? Then we're expecting the demand to go down. What's going to be cool and interesting here is to see what happens to the other partial derivatives when there's a link between these two demand. For the other two partial derivatives, del XA over del PB and del XB over del PA, these partial derivatives, a priori, they can be negative, positive, or zero. There's no fixed rules for them. But depending on the sign of those partial derivatives, we will be able to decide what type of relationship the two products are. So we're going to say that two products are competitive if the partial derivative del XA over del PB is strictly bigger than 0 and del XB over del PA is strictly bigger than 0. So in a nutshell here, what's going on? So if the price of the other product, so this is basically what those two partial derivatives are trying to measure, what happens to your demand if the price of the other product is going up? Well, if the price of the other products are going up and your demand is going up, it means that people are going to use their money to go to buy your product instead of the other one. So those two products are automatically in a competitive relationship. So if both partial derivatives, del XA over del PB and del XB over del PA are strictly positive, you're dealing with two products that are competitive. A nice concrete example for that is, for example, if you're thinking about beers for some reason, if you think about the Guinness beer or the Labatt 50 beer, if you're at the dépanneur, okay, and you have some cash and you're trying to decide which one you're going to buy, well, of course, if the price of Guinness is way higher than the price of Labatt 50, you're going to go for the Labatt 50 and vice versa. If the prices for the Labatt 50 for some weird reason goes up to the roof, you're going to use your money to buy your Guinness. So it's really, you're going to put your money on one or the other, and you're going to go typically, okay, for the one who's cheaper. Now you can have the reverse scenario. We're going to say that two products are complementary if both partial derivatives are strictly negative. So if del XA over del PB is strictly less than 0, and if del XB over del PA is strictly less than 0 also. So here the idea, very quickly, is that you basically need those two products. And if the price of one product is going up, then you don't have more money or to buy the other one, because you're just going to have less money overall. So when you have that relationship where both partial derivatives are 0 in that case, you're going to say that the two products are complementary. It's like me, for example. What do I enjoy? I need my beer and I need my makeup, to have a nice evening. Well, if the price of beer goes up, I'll just have less money to buy makeup. And if I have less money to buy makeup, I'll just buy less of it, and vice versa. If the price of makeup is going up, then the price of makeup is going up, and I need to buy it, then I'll have less money to buy beer, so I'm going to buy less of it. So here, beer and makeup is, of course, two products that are complementary and essential for a nice evening. All right, now let's go do an example with actual equations and looking at the sign of the partial derivatives. Example, let PA and XA be the price and the demand, respectively, for boxes of nicotine patches, and let PB and XB be the price and demand, respectively, for cartons of cigarettes. Suppose that XA is modeled by the equation 1,000 times the square root of PB plus 1 over e to the power of PA, and that XB is modeled by 2,000,000 times the ln of PA plus 1 over PB squared plus 1. Let's decide here if these two products are competitive or complementary, or if they have no special relationship according to our definition. So here, as an exercise, I'll let you do this. If you compute del A over del PB, you're going to get 500 over e to the PA times the square root of PB plus 1. And here you can see that the numerator, 500, of course, 500 here, that's a positive quantity. The exponential function, EPA, is also positive. The square root, here, remember, PA and PB are going to be strictly positive quantities. So the square root here is going to give me something positive. So everything is positive. The partial derivative with respect of XA with respect to PB is strictly positive. And now if we look at the other partial derivative, again here as an exercise, compute it on your own. If you compute del XB over del PA, you're going to get 2,000,000 over PB squared plus 1 times PA plus 1. So here again, if you do the sign analysis, the 2,000,000 here is again going to be positive. I'm going to use the same plus here. PB squared plus 1 that's positive. PA plus 1, that's positive. So the whole thing is strictly strictly positive, sorry, for all PA, PB that are strictly positive. So when both partial derivatives, del XA over del PB and del XB over del PA are strictly positive, we can conclude that these two products are competitive. So if the price of cigarettes goes down, you're going to go smoke your cigarettes. But if the patches of nicotine go down, you're going to go for that one instead. So just to conclude this section, one remark here. This is not part of the solution of that question. If the question is asking you to check if two products are complementary or competitive, there's only two partial derivatives to compute. But here's something that is pretty sweet here. If your question is done correctly, if your models are done correctly, what happens if you compute del XA over del PA and del XB over del PB? You're expecting them, both partial derivatives, to always be strictly negative. And you can do this here. So as an exercise, again, those are nice questions. As partial derivatives question, if you compute del XA over del PA, you're going to get minus 1,000 times the square root of PB plus 1 over e to the PA. And again here, minus 1,000, that's going to be negative. The square root is going to puke out something positive. Same thing here for the exponential function. It's always going to be positive. So overall, that partial derivative is negative, and we're expecting that. This is like always going to be the case. If not, something is fishy. So same thing for the other partial derivative, del XB over del PB. You have minus 4 million, so that's negative. Ln of PA plus 1, so if PA is strictly positive, ln of 1, it will be strictly bigger than 0, sorry, so it's going to be positive. So PB squared plus 1 squared, that's going to be positive. So overall, this expression is always going to be strictly negative for all PA, PB strictly bigger than 0. So, and this is again as expected. So you don't have to compute those partial derivatives, but then again here, this is just a nice exercise. If you do compute these two partial derivatives, they're going to be always, if the moles are good, they're going to be always strictly negative. But again, this is just a remark here. If the question is just to check if two products are complementary or competitive, you compute the partial derivatives del XA over del PB and del XB over del PA, and you check if both signs are positive or if both signs are negative. When they're both positive, they're competitive. When they're both negative, they are complementary. All right, for that section, that's it. That's all. Bye-bye.